This is the Pantheon in Rome. If you walk inside today, look up. You will see the largest unreinforced concrete dome in the world. It has stood there, exposed to rain, wind, and gravity, for nearly 2,000 years. It is pristine. No steel beams holding it up, no modern sealants protecting it, just ancient stone and ingenuity. Now, compare that to this. This is a typical highway overpass built in the 1960s. It is barely 60 years old, and it is already dying. The concrete is spalling, chunks are falling off, and the steel inside is rusting away. We spend billions of dollars every year just trying to patch these things up, knowing full well they will eventually have to be torn down and rebuilt. Here is the paradox that has haunted engineers, architects, and historians for centuries. We have split the atom. We have sent telescopes to the edge of the universe. We carry the sum of human knowledge in our pockets. Yet when it comes to the most basic building material on Earth, the very foundation of our civilization, we are somehow worse than a society that didn't even understand the germ theory of disease. For over a millennium, the secret of Roman concrete was considered lost. It was one of the great lost technologies of the ancient world, alongside Greek fire and flexible glass. For decades, modern science thought it had solved the puzzle. We convinced ourselves that the Romans just got lucky with their geography. We thought their secret ingredient was a specific type of volcanic ash found near Naples. We were wrong. The real secret was staring us in the face the whole time. It wasn't hidden in a lost scroll or buried in a tomb. It was hidden in the flaws of the concrete itself, imperfections that modern scientists laughed at and dismissed as sloppy work. But a groundbreaking study from MIT has finally cracked the code, and it changes everything we thought we knew about construction. The Romans didn't just build walls. They built living organisms. They engineered materials that can heal themselves. And today, we are going to uncover the chemistry, the history, and the future of this rediscovered technology. This is the story of how we lost and finally found the secret to building forever. To understand the genius of the past, we first have to ruthlessly examine the failure of the present. Why do our modern buildings crumble? It's not because we don't know how to build strong things. It's because we prioritized speed and cost over longevity. The material we use today is Portland cement. It was patented in the 19th century, and it conquered the world for two reasons. It's cheap, and it dries fast. In a capitalist world, speed is money. But Portland cement has a fatal flaw. While it has incredible compression strength, meaning you can stack a skyscraper on top of it and it won't crush, it has terrible tensile strength. If you try to pull it apart, twist it, or bend it, it snaps like a dry twig. To solve this, modern engineers marry concrete with steel. We embed steel rebar inside the concrete. The concrete takes the weight, the steel takes the tension. It seems like the perfect marriage, but like many marriages of convenience, it is destined for a messy divorce. The problem is oxidation. Concrete is naturally porous. Over time, tiny microscopic cracks form. Moisture from the air, salt from the roads, and rain seep into these pores. Eventually, that water finds the steel, and when steel rusts, it expands. Iron oxide takes up more space than iron. In fact, rusting steel can swell up to 4 times its original volume. This creates a massive internal pressure that pushes against the concrete from the inside out. It's a slow-motion explosion. Engineers call it concrete cancer. Once it starts, it is irreversible. This chemical inevitability ensures that most modern structures have a functional lifespan of only 50 to 100 years. We are essentially building disposable cities. Now, let's look back at the Romans. They didn't use steel rebar. They didn't need to. Consider the Roman seawalls at Caesarea Maritima or the harbors of Italy. These structures have been battered by saltwater waves for 20 centuries. In modern concrete, salt water is a death sentence. The chloride ions eat the steel and dissolve the cement paste. But in Roman concrete, the seawater actually makes it stronger. For a long time, the academic consensus focused on one magical ingredient, pozzolana. This is a specific type of volcanic ash found in the region of Pozzuoli, near Mount Vesuvius. The Romans shipped this ash all over the Mediterranean. Ancient texts were very specific about it. Vitruvius, the famous Roman architect, wrote a treatise called De Architectura around 30 BC. He explicitly praised this ash, saying it yields wonderful results and creates barriers that neither waves nor the force of water can dissolve. Pliny the Elder, writing in his Natural History, also marveled at how this dust, when mixed with lime and rubble, became a single stone mass impregnable to the waves. Modern chemistry eventually explained why. When you mix this volcanic ash with lime and seawater, it triggers a pozzolanic reaction. Over years and decades, this reaction forms a rare mineral called aluminum tobermorite. These unique crystals grow inside the concrete, weaving together like a microscopic root system. They provide a flexibility and toughness that modern concrete lacks. So for the last 50 years, the case was considered closed. The Romans had magic dirt. If we wanted Roman concrete, we just needed volcanic ash. But there was a massive hole in this theory, a logic gap that bothered a few observant scientists. The Romans built durable concrete infrastructure all over their vast empire. We find high-quality Roman concrete in North Africa, in France, in Spain, and in the Middle East, places thousands of miles away from Mount Vesuvius. They certainly shipped some ash, but they couldn't ship millions of tons of it to every remote outpost. Yet the concrete in those remote places still held up better than our modern bridges. There had to be a universal principle, a technique they applied to all their mixing, regardless of the local ingredients. Enter Admir Masic, a professor of civil and environmental engineering at MIT, and his team decided to look closer at the concrete itself, specifically at the parts everyone else ignored. If you cut open a piece of Roman concrete, you will see these millimeter-scale white chunks scattered throughout the gray matrix. For decades, geologists and archaeologists called them lime-clasts. The standard academic explanation for these white chunks was, frankly, insulting to the Romans. The experts said the Romans were sloppy. The theory was that the workers didn't mix the mortar well enough, leaving unmixed lumps of lime floating in the cement. It was viewed as a quality control failure, a defect of ancient primitive manufacturing. Professor Masic didn't buy it. Think about who we are talking about. These are the Romans. These are the people who built aqueducts with gradients so precise they only dropped a few inches over miles. These are the people who built the Colosseum and a road network that spans continents. Would these same master engineers really do a sloppy, lazy job mixing the concrete for their most important imperial temples? It didn't make sense. So the MIT team took samples from the city wall of Privernum, Italy, and subjected them to high-resolution multi-scale imaging and chemical mapping techniques like Raman spectroscopy. What they found completely rewrote the history of construction materials. These white chunks weren't unmixed lime. They were a specific form of calcium carbonate that had been formed at extreme temperatures. This chemical signature revealed the true secret process of Roman engineering. It's a technique called hot mixing. Here is how it works. Modern concrete is mixed cold. We take chemically treated cement powder and mix it with water, an aggregate. It's a room temperature process. But the Romans did something dangerous. They used quicklime, calcium oxide. Quicklime is a volatile, caustic substance. When you add water to quicklime, it triggers a violent exothermic reaction. It explodes with heat. The mixture can instantly reach temperatures of over 200 degrees Celsius or 400 degrees Fahrenheit. This was a hazardous job. Roman laborers risked chemical burns and heat exhaustion. But this risk was calculated. The extreme heat did two things. First, it significantly sped up the curing and setting times, allowing the Romans to build faster. But secondly, and most importantly, this heat prevented the lime from fully dissolving immediately. It created a brittle particle architecture. It froze the lime into those little white clasts we see today. These clasts weren't bugs. They were a feature. They were essentially calcium batteries waiting to be activated. This is the mechanism of self-healing. Imagine a crack forms in the Roman concrete. Cracks are inevitable in any stone material due to settling or seismic activity. As the crack expands, it travels through the path of least resistance. In this concrete, that path leads directly into the brittle lime clasts. The crack splits the clast open. Then, nature takes its course. When it rains or when seawater splashes against the wall, water flows into the crack.
In modern concrete, this water would start the rusting process. But in Roman concrete, the water hits that reservoir of reactive calcium. Because the lime was hot mixed, it is still chemically unstable. It dissolves into the water, creating a calcium-saturated solution. As this solution flows through the crack, it recrystallizes. It turns back into calcium carbonate, essentially limestone. It literally grows new stone to fill.
In modern concrete, this water would start the rusting process. But in Roman concrete, the water hits that reservoir of reactive calcium. Because the lime was hot mixed, it is still chemically unstable. It dissolves into the water, creating a calcium-saturated solution. As this solution flows through the crack, it recrystallizes. It turns back into calcium carbonate, essentially limestone. It literally grows new stone to fill the gap. It functions exactly like a blood clot sealing a wound or a scar forming on human skin. The MIT team proved this in the lab. They took blocks of authentic Roman-style hot-mixed concrete and deliberately cracked them. Then they ran water through the cracks. Within 2 weeks, the water stopped flowing. The cracks had completely sealed themselves. They ran the same experiment with modern control samples. The water never stopped. The cracks only got wider as the water eroded the edges. The difference is philosophical. Modern engineering tries to resist nature. We try to build a fortress that is too hard to break, and we try to seal nature out. But nature always wins. Water always gets in. The Romans, on the other hand, built structures that collaborated with nature. They anticipated the damage and built a system that used water, the very agent of destruction, as the catalyst for repair. They turned the enemy into an ally. So the trillion-dollar question is, why aren't we using this everywhere? Why are we still building bridges that rot? The answer is that we might be on the verge of a revolution. The environmental cost of our current method is staggering. Cement production alone accounts for about 8% of global greenhouse gas emissions. If the concrete industry were a country, it would be the third largest carbon emitter in the world, right behind China and the US. We cannot stop building, but we can change how we build. If we can use this hot mixing technique to build bridges, tunnels, and seawalls that last 150 years instead of 50, the impact would be massive. We would reduce the need for demolition, the need for new raw materials, and the massive carbon footprint of rebuilding infrastructure every few decades. Professor Mazik and his team are already working on commercializing this formula. Startups are beginning to test self-healing additives based on this ancient chemistry. We aren't just looking at the past for nostalgia, we are looking at it for survival. History is often presented as a straight line of progress. We assume that because we live later, we must be smarter. But the story of Roman concrete is a humbling reminder that progress is not linear. Knowledge can be lost. Entire civilizations can forget things that were once common knowledge. It took us 1,500 years to rediscover what a Roman laborer knew by heart, that sometimes, to build something that lasts forever, you have to add a little bit of heat. What other ancient technologies do you think were superior to what we have today? Damascus steel with its carbon nanotubes, or perhaps the precision of Egyptian stone cutting? Let me know in the comments below. If you enjoyed this deep dive into the lost science of the ancient world, make sure to hit that subscribe button and turn on notifications. We have many more mysteries to uncover. Thanks for watching.